The problem asks us to compute the bounds on the sum of the first n square roots. Well, first of all, let's try to understand the motivation behind this problem. Instead of thinking of the sum of the first n square roots, let's think of a simpler sum, which is the sum from y equals 1 to n of I. So it is 1 plus 2 plus 3 plus n. For this sum, we have a closed form, which is n times n plus 1 over 2. So if you want to calculate the sum of the first 120 numbers, you just plug in 120 to the formula and you've got it. The same thing goes, for example, for the sum from y equals 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared plus n squared. This formula is a little uglier, but we do have a closed form for it. So it's n times n plus 1 times 2n plus 1 over 6. Okay, cool. But what we want here is the sum of the first n square roots. We want the sum from y equals 1 to n of the square root of n. Now for this sum, we do not have a neat closed form like the ones we've just described here. If you ask me what is the sum of the square roots of the first 120 numbers, I do not have a formula in which I can plug in 120 and give you a quick and precise answer. So what can we do here? What we can do is go with the next best strategy, which is compute the lower and upper bounds on the sum. Suppose we have a graph for a function f of x. We've got n here and f of n here, and then we have n minus 1, n minus 2, etc. And here we have 2, 1, and 0. So f of n minus 1, f of n minus 2, f of 2, and f of 1. Now let's build rectangles in which the height is f of x, and remember that the base is always 1. This is f of n, this is f of n minus 1, f of n minus 2, f of 2, and f of 1. Let's draw a curve that starts from the right corner of the f of 1 rectangle, goes through f of 2, f of n minus 2, f of n minus 1, and f of n. So we have all these points in our curve. This is f of x. Since this is a non-decreasing continuous function, we can use a theorem that tells us the following. The sum from I equals 1 to n of f of I is greater than or equal to f of 1, which is this rectangle. This is f of 1 plus, and let me give myself some extra room here. Well, looking at the graph, what do I need to add to f of 1? Now I need to add the area under the curve. And I can do so using an integral. So the integral from 1 to n of f of x with respect to x. This is the lower bound of my sum. So my sum is at least this. And if you look at the graph, it makes sense because our curve is leaving out these parts of the rectangles here. So that's why it is a lower bound. Now we need an upper bound. So of course this sum is also less or equal than something. Let's remove this shaded area. And imagine that we are now going to get these points and shift them to the left. 1 unit to the left, all of them. What will happen then? We will now have a different curve, which I'll try to draw here. It is this one, or something like that. And since we only shifted it to the left, the area under the curve stays the same. But now this is the area under the curve. And instead of summing f of 1 as we did before, now we need to sum this part, this rectangle, which is f of n. So our upper bound is going to be, again, the integral from 1 to n of f of x in respect to x, but now plus f of n. Notice that these terms are the same. Cool, so now we can go ahead with our problem. I'll leave it here as a reference, and then let's first find our integral. So what we want is the integral from 1 to n of square root of x dx, and this is x to 3/2 over 3/2, evaluated at n and 1, and that equals 2/3 times n to 3/2 minus 1. Now let's find our bounds. We have our integral, then let's use it here. So first, what's f of 1? It is the square root of 1, which is just 1. So I'm using already our f of 1 here, and now we need to add this. So 1 plus 2/3 times n to the 3/2 minus 1. So this is less or equal than the sum from y equals 1 to n of the square root of I, and the sum is less or equal than f of n this time, which is the square root of n, plus again the result of our integral, which is 2/3 times n to 3/2 minus 1. Simplifying, we have 2/3 times n to the 3/2 plus 1/3 less or equal than the sum from y equals 1 to n of the square root of I less or equal than 2/3 n to the 3/2 plus the square root of n minus 2/3. And these are our bounds, but let's go a little further and explore another concept here. Something you should notice is that the term 2/3 n to the 3/2 is repeated both in the upper bound and in the lower bound, right? So if we did not have these other terms, then actually we would have a precise sum. It would be exactly this term. This means that the remaining terms, 1/3 in the lower bound and the square root of n minus 2/3 in the upper bound, these are what actually create the interval. And this interval is what can be considered our error. And we often call this delta n. So we could say that the sum of I equals 1 to n of the square root of I equals this term, which is 2/3 of n to the 3/2 plus delta n, where 1/3 is less or equal delta n, which is less or equal than the square root of n minus 2/3. So our error is between 1/3 and root n minus 2/3. Now to wrap it up, let's talk about growth. Growth of the bounds of our answer and growth of the gap or our error. How fast does our error grow? Well, it is bounded by square root of n, so it does get bigger as n grows, but it grows as square root of n. While the sum, our bounds, grow as n to the 3/2. And the thing is, n to the 3/2 grows faster than square root of n, which means that as n grows, our answer grows faster than the error. So for very large n's, the error becomes negligible and our sum, or the approximation of our sum, becomes extremely accurate. Graphically, if you wish, you can think that that kind of tube we had for our bounds gets wider as n grows, but compared to the size of the sum itself, it becomes smaller and smaller. We can represent that with the tilde notation, so our sum tilde 2/3 of n to the 3/2, and that's all. We got rid of the delta because the tilde notation is telling us that everything else is getting smaller and smaller as n grows. In other words, the limit as n goes to infinity of 2/3 of n to the 3/2 plus our delta n divided by 2/3 n to the 3/2 equals 1. This is kind of a formal definition for our tilde.